old optimization problems with convergence results. So to tell you a little bit about Aniket, Aniket is a pre-doctoral researcher at Google Research. Prior to this, he was an undergrad at IIT Kanpur, where he pursued electrical and mathematics. Aniket is highly interested in high-dimensional statistics, theoretical CS, ML theory, where he uses tools from probability theory, functional analysis, and geometry. So without further ado, I'll hand it to Aniket for your talk.
Thanks, Ram. So yeah. So I'll be talking about this classic problem of sampling from a Gibbs measure. So you have a very high-dimensional probability distribution on RD, whose density, which admits a density with respect to the Lebesgue measure, and you know this density to a normalizing constant. So you have e to the minus f. So the density is proportional to e to the minus f, where you have some oracle access to f. So say its values or its gradients. And this is a fundamental problem in machine learning, say Bayesian inference and these recent generative models, and like Kannan's classic work on algorithmic geometry and volume computation shows up there. And like even in statistical physics, there's like classic partition function estimation and these problems. And again, like if you're familiar with the classical theory of optimization, again we have this dichotomy that there is a hard case. Yeah.
So should f be thought of as a loss function over RD, where or a potential function over RD, and so sampling from it?
Instead of sampling from instead of optimizing a function, what you're trying to do is you have its negative log likelihood basically.
I see. So you're just translating a regular function into the negative log likelihood of the same function. Does such a negative log likelihood translation exist for every function?
I mean, think about Bayesian inference, say, like you have a prior over your parameters, and then your data given parameter is specified by some likelihood model, and you want to compute the posterior. And this posterior actually calculating the constant that will show up in the denominator of Bayes' theorem is intractable. It's a high-dimensional integral. So, but if you just take log p, this constant does not depend on the parameter. So the log likelihood is a very tractable function.
Right. So what I'm asking is, for what functions G does there exist e power minus fx such that it is?
So
or does it set for all?
So just like in optimization, like optimizing a convex function is hard. Optimizing a convex function is easy, and a non-convex function can be hard. Similarly, you have this dichotomy that like if f is convex, sampling from e to the minus f can be computationally tractable using MCMC methods. However, if f is non-convex, this problem is actually sharp p hard in general. So just like non-convex optimization is NP hard in general, this is the counting version of that problem. Yeah. And this is such a broad complexity class is that if you have a sharp p hard oracle, if you have an oracle for sharp p, then the entire hierarchy collapses. So
yeah, can you just click on the screen? Maybe that.
Yes. Yeah. So yeah, if it's basically if your negative log likelihood profile is very multimodal, you'll have, and non-convex, you'll have a hard time sampling, and this will take exponential time in general. And whereas if it's like nice unimodal and convex, you can sample it from like using various MCMC algorithms. And this is again analogous to optimization, where you have the convex optimization is easy and non-convex can be hard. So the classical algorithm for this, yeah.
And from my understanding, for the non-convex stuff, there is no guarantees that can be given except local.
Yeah, but like for given the progress on this, so theory for sampling has considerably lagged theory for optimization. So we don't even have a nice definition for what would local optimality even mean in sampling. That is also a topic of debate. Just like in optimization, you can say, okay, you can talk about the complexity of making the gradient small, and that translates to maybe something meaningful. But in sampling, like what's a local metric is appropriate is also not very obvious.
So convergence, say xt minus 1.
But like that can get you stuck in like a. So there's something called getting stuck in a metastable state, which I'll come to very soon. So yeah. So for like if your potential or your Hamiltonian is differentiable, classical algorithm for this is Langevin Monte Carlo, which is basically you have a gradient descent plus you add a large Gaussian noise plus like if you're doing gradient descent with step size eta much less than 1, so you add a plus √2 eta Gaussian noise. So what basically it does is it sort of moves you towards the minimum of the potential, but the Gaussian noise also promotes exploration. So you actually, instead of minimizing, you actually sample. And the theory behind this can be seen as that this is the straightforward Euler discretization of a very famous SDE called Langevin diffusion. And so, like in continuous time, like if you take eta tends to 0, so this becomes instead of a ordinary differential equation, this becomes a stochastic differential equation. Yeah.
So from my understanding, grad FXK is pretty hard to get. So you might want to do stochastic versions of it.
Yeah.
So do stochastic versions of such gradients also exist?
Yeah, exactly. That's exactly what SGLD is actually. And this thing is this is well known. This is a Markov process whose stationary distribution is your target pi star, which you want to sample from. And yeah, so as t tends to infinity, law of xt converges to pi star. And if pi star is nicely behaved, it has certain isoperimetric properties, this convergence can be made very rapid. It will happen exponentially fast. But however, as you said, that in many large scale problems, you can't. Like directly computing grad f accurately is either expensive or it can even be intractable.
Yeah. So in the previous slide, like what kind of noise can you assume? So one is Brownian, but is it necessary for Langevin dynamics that I use only Brownian noise? Or
by definition, the Langevin dynamics SD is defined as.
Are there other forms of noise that are used and that will lead to?
You can come up with like more complex processes, and then you can show that okay, this is a Markov process, or it may be it is a Markov process whose stationary distribution is pi star. Like this is not the unique process for sampling from this, but yeah.
And just to understand Brownian motion, it is multiple steps of Gaussian system.
Yeah, basically independent Gaussian, like it's a process with independent Gaussian increments, and yeah. Yeah, any like non-overlapping time input intervals T2, T1, T2, T3, T4, T3, BT4 minus BT3.
So it's the limit of multiple Gaussian.
Yeah, you can loosely think of it that way. Like all of its increments will be independent Gaussians for non-overlapping time intervals. Yeah. So as you were saying that, like in many problems, this computing grad f accurately can be either expensive or intractable. So the other thing, but what people do is that you just estimate grad f using a stochastic gradient oracle. And this gives rise to what is popularly known as stochastic gradient Langevin dynamics, which basically replaces the full gradient computation with a minimal gradient estimate, and the Brownian noise injection remains as is. However, like this is what is practically used almost everywhere. However, unlike Langevin Monte Carlo, whose theory is considerably well developed, the convergence theory of SGLD is like much less understood.
So you asked that noise be injected. Is the noise due to the stochastic nature? Or
no, this noise is intrinsic to the fact that you're discretizing a Brownian motion. And this comes from the Brownian motion increment. This is completely independent of the stochastic gradient noise.
And the stochastic gradient noise will come from error terms of the second.
Yes. And like one of the key objects of our study would be how these two can interact with each other.
And so how is B chosen? What is B and how is it chosen?
This is just the batch size, like dealer's choice. And yeah, so another this algorithm sort of falls into this family of algorithms called Markov chain Monte Carlo algorithms, where you simulate a Markov chain to sample approximately from a target distribution. So there's this other class of popular algorithms called interacting particle dynamics, where what you do is you take a system of n particles and you evolve them across time such that after a sufficiently long time, the empirical distribution of these n particles would sort of approximate your distribution, right? Yeah.
Sorry, if you go to the previous step, you said the convergence of this equation is not very well known. But the only additional part that's not well known is probably the root 2 eta epsilon, the noise.
No, the theory, like the way you'd handle, like this is not optimization. You no longer want to show convergence to a point. You want to show the convergence of the law of this whole process, like law at time t of this process too. So like it's a whole different volume, and which is why just adding this changes a lot, unless you look at it the right way. Yeah, so this is sort of an aesthetic displeasure that existed in the literature. GD and it, like, so I'm jumping ahead here, but like for example, like in optimization, gradient descent and stochastic gradient descent, you can analyze under the same assumptions, right? If it, like say PL inequality, it's sufficient for convergence of both GD and SG. The rates might differ. However, like prior to our work at least, in sampling, the assumptions you'd need for showing convergence of SGLD are inherently much stronger than the assumptions you'd use for showing convergence by LMC. And there's this other algorithm called Stein Variational Gradient Descent, which greatly departs from this MCMC framework by simulating a set of interacting particles, such that like the empirical measure of these particles after a long enough time would closely approximate your distribution. So like if this were being animated, what would happen is these particles would repel from each other and sort of approximate this distribution well. And practically, like the theory for this is nearly non-existent, but practically this outperforms MCMC methods in many use cases, even for small n. But understanding its convergence, which is also very recent, was only restricted to the mean field or interacting or infinite particle limit when you assume that the number of particles tends to infinity. Another very interesting thing about this algorithm is that, like, except for the initial random sampling of the particles, these updates are entirely deterministic. So you're sampling from a distribution with purely deterministic updates.
Can you give an example of where SVGD might be used, like in practice? Like, is this
Bayesian inference, like learning ensembles of neural nets, say?
And what do the interactions between particles look like? Like,
they are like if you take a say if you take an RBF kernel here, e to the minus gamma x minus y square.
So interactions are
repulsive. Like you want them to gather around this term sort of encourages gathering around the minimum of f, but the second term encourages each particle to repel each other, so that promotes diversity, and the combination of the two lead to sampling. And like upon closer analysis, we'll see this term is actually related to the minus grad f term that you see in Langevin, and this term is arising due to the rounding motion.
So in a sense, it's so k can be thought of as some sort of distance measurement.
Yeah, k is a kernel basically, any kernel you use.
And f can be thought of as some loss function.
Yeah, it's negative log activities. And yeah, so nice thing about this is at least interesting thing about this is that the time evolution in between steps is entirely deterministic. So this is closely connected to a phenomenon in physics called propagation of chaos. But why are we even discussing this? So SGLD and SVGD, clearly they're two very different algorithms, and the open questions related to the two are also very different. So firstly, should we even bother with a unified treatment, or is that even possible? Actually, it is possible if you interpret sampling as an optimization problem over a special kind of space. And even if you do that, is there any common thread between the two? Which also we shall see is true, as we can interpret both as stochastic approximations. And we'll do this by understanding the Riemannian structure of the Wasserstein space and understanding what Wasserstein gradient flows are.
So from my understanding, SGLD applies to single particle, but
SGLD, yeah, it's a single particle
that's getting sampled.
Yeah.
And SVGD comprises of many particles.
So SVGD comprises of many particles, and the empirical distribution of those n particles should closely approximate the target in some appropriate metric.
And how are you going to, to give a precursor to what you're going to say, how are you going to merge the two?
like we are going to see that like both are actually doing optimization in like both are just different optimization algorithms for the same optimization problem
because
in the space of problem.
In the first case, there's only errors.
Yeah. So, but like they're basically two different optimization algorithms for the same optimization problem. Is what I'll try to illustrate. So we'll look at this object, this space P2 of RD, which is the space of all probability measures on RD whose second moment is finite. And if that happens, we can equip this space with the Wasserstein-2 metric from optimal transport. So a natural metric for the space is like to take the minimum overall couplings of two probability densities, two probability distributions mu and nu, and you basically minimize the expected L2. Yeah. And when your target is also has finite second moments, you can see that sampling actually becomes an optimization problem over P2. You can treat the sampling problem as a minimization of the KL divergence. Yeah, and this has a unique meaning. So if the law of whatever Markov chain or whatever process you're running, say its law is mu, you'd want that the KL between mu and pi star to be minimized. And this problem has also the nice property that pi star is the unique minimizer. There are no spurious minima.
I didn't follow this. Can you go over this again? So I understood what is the Wasserstein metric. So mu and mu are probability measures over RD.
Yes.
And P2 is what?
P2 is the space of all probability measures on RD. So mu and mu are elements of P2. So I consider a space where each point is a probability measure. And this is an infinite dimensional space. And I can make this a metric space by equipping it with the Wasserstein-2 metric.
So P2, so every point in P2 is
a probability measure.
An infinite dimensional space, which denotes the probability measure over RD.
Yes, which denotes the probability measure. Yeah, it's the set of all couplings. So like it's the set of all distributions on RD times RD, so that the first marginal is mu and the second marginal is mu.
Other matrices, not just scale.
Yeah, you can, and they will give you very different algorithms. Like we see that like natural algorithms that people have already used actually can be interpreted as some optimization algorithms over KL. Similarly, you could use some other metric, it would give rise to like completely different algorithms. But whether you can actually implement it, like whether it's even computable or not, is a separate question. So yeah, so whatever algorithm you use, or like whatever Markov process or whatever procedure you're using, its law should minimize the KL divergence to your target. And this has the unique minimizer.
So sorry, go back to the previous slide. So what I'm trying to say is, let's say there are 2 points mu and nu on RD.
Yeah.
No, sorry, on this infinite dimension.
Yeah.
So like getting from mu to nu, there is some sort of distance function. You could also use other distance functions.
The distance, the equipping it with the Wasserstein-2 distance is important, because what I'll use is that this space is not just a metric space, it also admits a manifold structure. You can talk about tangent spaces and things like that. And that is sort of like.
And in this equation, what is pi star? Like min over what?
Min over mu. It's the min over all measures in P2 of RD. And h of mu, where h of mu is a log, like treated like a objective function, is KL between mu and pi star, where pi star was e to the minus f. So this is like I can treat sampling like an infinite dimensional optimization problem on this space.
So why is pi star not mu? You want to minimize it?
Yeah, I do want to minimize it, and it will be minimized at. What I'm saying is like, yeah, the argument is pi star, and that's the unique argument basically.
By definition.
Yeah, by definition. Yes. So all I'm saying is that the sampling problem can be just seen this way. I'm not saying that this will this gives you some solution. This is just a way to interpret the sampling problem.
So this pi star is what?
This pi star is the pi star we started with, e to the minus f, whose normalizing constituted.
What's the relationship between this Wasserstein metric and this
optimization problem. What's the relationship between the metric you define here and the optimization problem?
So what we see is that what we later see is that because of the metric we chose here, we will be able to equip with this space with some Riemannian structure. So we'll be able to talk about gradients and gradient flows and tangents on this space itself. And that is like the properties of the manifold properties are very sensitive to the metric. So if you would replace it with Wasserstein P, basically it controls the geometry of the problem essentially. Which again, like think of it like mirror descent kind of problems, like something may be smooth in the like LP geometry, but not in the LP. Yeah.
So no assumptions on pi star. So for example,
not yet.
You don't need compact spaces.
Not yet. I will be a little like some assumptions may be under the rug, but at this point, like we are just assuming pi star as finite second moment. Yeah. So there's this very celebrated result by Felix Otto in 1988 that this space P2 of RD actually admits a Riemannian structure. You can talk about at any point, you can talk about a tangent space to this point. And in fact, you can characterize this tangent space like for any point mu on P2 of RD, the tangent space is actually a closed subspace of L2 of mu, which is the space of all square integrable functions. And yeah, you also have an explicit characterization that isn't of much help. But the nice thing to see from here is that the tangent space inherits the inner product structure of L2 of mu. So you not only have a tangent space, you can talk about inner products on the tangent space.
And you need this tangent space because you're taking gradients over.
Because of this tangent space, you'll be able to talk about gradients of functionals in this space. You can not only treat this as an optimization problem, you can think of it as a gradient-based optimization. Like you can use gradient-based algorithms.
And you're going to show that the gradient also lies on this space.
Gradient will lie on the tangent space. Yeah. Basically, because the tangent space now has inner products, you can define gradients and talk about gradient flows and even define what gradient descent means in the first place. Without this manifold structure, you wouldn't be able to do that.
Why is it CC infinity of RD? Should it not be CC infinity of R infinity?
No, this is CC infinity. This is how the tangent space is characterized, and this should be a subspace of L2 of mu.
I'm asking whether L2 of mu is an infinite dimension.
L2 of mu is an infinite dimensional space, but individual elements of L2 of mu are functions from RD to R, right? And yeah, so the tangent, what the key message here is that the tangent space inherits the Hilbertian structure. Sure. This one? Yeah, here. This is not important. What's important is that this is a closed subspace of the tangent space at any point is a closed subspace of L2 of mu. Okay, and this has like, as I said, this has amazing consequences. Now you can talk like for any functional f from P2 of RD to R, you can talk about gradient differentiability of such functions, and you can define gradients. You can study curves on this manifold and gradient flows. And in essence, this manifold structure is what allows you to transfer insights from the theory of optimization on RD or the theory of optimization on arbitrary finite dimensional manifolds to this sampling problem.
So to recap what you have done, you took fx, you took a probability distribution e power minus fx. This translates to one point in the infinite dimensional space.
Yes.
And then you are considering like gradients of these points on the infinite dimensional.
Now considering the optimization problem on this infinite dimensional space, that like where I want to
the Wasserstein gradient.
No, this is not the Wasserstein gradient. This is just an optimization. There has
what is the Wasserstein?
I'll come to that. Wasserstein gradients are gradients of functionals in this space. Now that I have a Riemannian structure, I can take gradients of those functionals, right? And such gradients of functionals defined on P2 of RD would be Wasserstein gradients. Yeah.
There should be some very minor assumptions on F, but yeah. But under most standard assumptions that you would need anyways to prove convergence, you'd. I mean, as long as the tails don't behave like your tails aren't super heavy, you're good. Yeah. So you can transfer insights from optimization on RD because you now have a manifold structure.
Except that now you're working with R infinity.
It's an infinite dimension space, not clear if it's like, it need not be R infinity. It's much more complex than that actually.
The metric, so this Otto's result proves that that is a metric space, and therefore
no, the fact that it's a metric space is obvious by definition. Otto's result proves that it has a Riemannian structure, and Otto's result gives you an explicit characterization of the Riemannian structure. So you can talk about tangents and things like that. How is it to? So
right there.
Yeah.
Here. Down there, on the other side.
Yeah. So the Wasserstein gradient would be defined as follows. So if you have a functional f from P2 of RD to R, and let mu t be any curve in P2 of RD that passes through mu at point 0, and its tangent vector at t equals 0 is v. So one characteristic example would be something like this, that suppose v is some function at L2 of mu, right? And ut equals I plus identity plus tv push forward mu.
So can you write little r?
V is some function in L2 of mu, and mu is identity plus t times v push forward of mu. It's easy to check that this curve always lies in P2 of RD.
What do you mean by push forward?
If x is distributed as mu and y equals x plus y equals f of x and law of y, when y is distributed as push forward. Push forward in the sense of just change of variables. Yeah. So this is one example. So, but this holds generally for any curve. So for any curve mu t that satisfies mu naught equals mu and whose tangent vector at t equals 0 is v, and so Wasserstein gradient of f at mu is the unique tangent vector that satisfies this property that the derivative of f of mu t at t equals 0 is the inner product of the Wasserstein gradient with the tangent vector v. This is like the analog of this in RD would be like if you had some function v and you have some curve xt such that x dot 0 was v of xt would actually equals this is just the Wasserstein space analog of this.
Would it x dot 0 equals to v? V is a point or like is a function?
Suppose xt was a curve in RD and f and v is some function from RD to R. Then right, this would just be and x0 equals x. This would just be grad v of x. I'm just porting that to P2 of RD. Yeah. And this holds in general for at any time t for such that for any curve whose tangent vector at time t is vt, this relation holds in general. And here's one fact that I'll use without proving. Like you can refer to Ambrosio, Gillian's various book for this, that for the KL divergence, the Wasserstein gradient is exactly the gradient of log mu over pi.
So from my understanding, just to recap what you've done here, you're looking at mu t as a point, and then vt is like the sort
mu t as a curve, yes.
Mu t is a curve, and vt as the derivative. Sorry, the velocity of that curve.
V is the velocity. Vt is the velocity of that curve at each point. Yeah.
Or rather than
yeah. For any curve, the velocity would belong. For any curve on a manifold, the velocity would be an element of the tangent space. And so f of mu t is essentially just a chain rule for P2.
And then you're translating this. So this is the curves itself, and then you're translating this using your push forward to
just now evaluating of my function along this curve. So that gives me a function from R to R. This I can differentiate. And this will come out to be something like this. So the unique vector that satisfies this for any possible velocity field is the Wasserstein gradient. And for the KL divergence, this has a closed form expression that the Wasserstein gradient of the KL divergence is grad log mu over pi. Grad log mu over pi star. Notably, this does not depend on this quantity does not depend on the normalizing constant. If pi star is e to the minus f by some normalizing constant, like because of the log, and then the gradient, the normalizing constant would disappear entirely. Yeah.
Saying that this Wasserstein gradient is like the natural way of defining the gradient on this.
Yes. Yes.
Is this how Wasserstein is defined, or is it a natural?
This is one of the ways to define it. You can also define it like from PD perspective via the continuity equation. Okay, this is a more geometric definition of the Wasserstein gradient that aligns more with like how you do calculus on
This is
RD.
called the Wasserstein gradient of the function f.
This is called the Wasserstein gradient of the functional f. Yes.
And given a Wasserstein gradient of a functional f, it does not change for every curve vt.
And this is independent of the curve.
Independent of the
and yeah, this should be satisfied for all curves for all possible tangent vectors.
So you're somehow translating like the gradients along this curve mu t to gradients along d by dt of f of mu. Like it's a, you know, if you think of f as a
because the curve is changing, the p is changing. Yeah. So our first application of this would be to like analyze finite particle convergence of SVGD, which was a long-standing open problem. So just like you can have, so now you can, since you can define Wasserstein gradients, a natural question to ask is, okay, let's do Wasserstein gradient descent. So suppose again you have this functional KL divergence, and you know that the Wasserstein gradient of this is this. So just by writing and suppose you have a discrete trajectory in P2 of RD that mu t plus 1 equals I minus gamma gt push forward mu t, right? And so just by a Taylor expansion argument in this space, so h of mu t plus 1 minus h of mu t would up to the leading order be at most gamma times gt minus gamma times gt times the Wasserstein gradient, because the velocity field of this is sort of minus gamma gt. It's a piecewise constant velocity field. So you can just substitute it into this expression. Integrated for small times, so approximately it will be this to the leading order. And for steepest descent, you ideally want GT to be exactly grad log mu t over pi star, right? However, this like using just samples from xt from mu t, if you don't know the law of mu t, this quantity is not computable. So
from my understanding, you also don't know pi star.
You also don't know pi star, but you know f, and this quantity is just.
You know f.
You know you have oracle access to f, so this quantity is just grad f, right?
You have oracle access to f.
No, pi star is just fixed e to the minus f. So minus grad log pi star is just becomes grad f, and the normalizing constant disappears because of the gradient. So the next best thing to do is fully project, like instead of taking the steepest descent direction, take the steepest descent direction in some subspace, and hopefully that will be more tractable.
So you don't have noisy access to the gradients, you have exact access.
For now, let's assume we have exact access. For SGLD, we don't have exact access, we have noisy access. So we'll project it into, like, the space of choice we'll take is like the RKHS of some reproducing kernel. And so consider some reproducing kernel which is like square integrable, and let's denote its d-dimensional RKHS as k, which is basically it's RKHS times, like it's the product RKHS, basically d times d4 product RKHS.
So basically k is just a distance.
Yeah, k is just consider the Gaussian kernel, for example, and it has to satisfy some property so that like it's a reproducing kernel. So the associated Hilbert space has continuous evaluation functional. And if this square integrability property is satisfied, it's easy to show that the inclusion operator from k to L2 of mu for any mu, like if this square integrability is satisfied, it's easy to show that k is a subspace of mu, or k is a subspace of L2 of mu for any mu in w.r.t. So you can define an inclusion operator that goes from your RKHS to L2 of mu. And you can also talk about the adjoint of this operator that satisfies this. Since both of these are inner product spaces, each equipped with their own inner product, you can talk about the adjoint of this operator. So for any f in the RKHS and for any g in L2 of mu, so inclusion f times g, the inner product in L2 of mu, would be equal to f times inclusion conjugate g in the inner product, in the k inner product.
So for me, this last equation is slightly more understandable. So what it's saying is basically, given g of x, you're just taking distance from x to all other.
No, but like this is the adjoint operator, and just like it just happens to happen that like this this inclusion adjoint operator is exactly representable in this fashion. Okay. What's important is this property, like. So since that inclusion operator is a well-defined operator between two Hilbert spaces, it must have an adjoint. K, like if the kernel is nice and if the kernel just satisfies this integrability property, K is a subspace of L2 of mu for any mu.
So in the first equation, basically your f is equal to K, and
the first equation. This equation?
That's translating to the last, because I understand the last one.
The adjoint one, all I'm saying here is that an adjoint must exist. Since I'm not saying anything about, all I'm saying is that there must be an adjoint because K is an inner product space and L2 of mu is an inner product space, and I is an operator from K to L2 of mu, so you must have an adjoint operator from K to K. And this adjoint operator is also representable in closed form as a convolution. So now we'll limit our search space to just RKHS, to this RKHS. So we'll only search for GT equals inclusion mu t ft, where ft belongs to K, right? And then just by taking an adjoint, you can see that the steepest descent direction would be the adjoint inclusion of the Wasserstein gradient.
And are you able to assume certain types of kernels, or are you moving K?
A K just has to be a reproducing kernel for now.
You're not assuming the Gaussian class.
No. And yeah, so the steepest descent direction instead of just being the Wasserstein gradient would be now a kernelized Wasserstein gradient. And the nice thing about this kernelized Wasserstein gradient is like, if you consider this function h of xy equals k of xy grad f of y minus like grad with respect to the second argument k of xy. This by integration by applying one step of integration by parts, you can show that this kernelized Wasserstein gradient is exactly equal to expectation, like exactly equal to this h mu of x, where you just for the y you take an expectation over mu. So previously you needed to compute the Wasserstein gradient, you needed actually the access to the law of mu, whereas now you just need to be able to integrate with respect to mu, or like approximate integrals with respect to mu. So
you get a much more tractable procedure at least. So instead of a Wasserstein gradient descent, you're now doing a kernelized Wasserstein gradient, which seems more tractable. And this, like,
but there's still you need exact access, and I mean non-noisy, and
you need exact access to F, and you need to be able to integrate
and
with respect to with respect to mu. But you don't need access to, you don't need to know the law of mu exactly. And this integral will replace it with an like
because you're only interested in points where it contributes.
No, I mean we'll just straight away, like, because we can't exactly compute these integrals, we'll straight away approximate it with finite samples. So this kernelized Wasserstein gradient descent, which for now is not an algorithm, it's just a procedure you get, and this admits this is very nicely interpretable. You've seen this just and this now you can prove convergence of this thing, this process in some metric called the kernel-Stein discrepancy, which is a well-studied metric in statistics. And the proof of this is very similar to the proof of convergence, of gradient descent to a stationary point. So, but like, what does any of this have to do with SVGD? So now, obviously, this kernelized Wasserstein gradient descent, these push forwards aren't computable in closed form. So if you do a particle approximation, if you take mu t is approximately equal to some mu hat t, where you approximate it with Dirac deltas, so you get a resulting trajectory mu hat t.
We have a question from online. Ayush asks, is the convergence guarantee asymptotic, or are they looking at finite step?
We have non-asymptotic 1 over t. D to 3 by 2 over root t, something like that. Yeah. But in the population limit, you're assuming like these you can calculate exactly. So it's non-asymptotic in time, but like continuous in space in some sense. And yeah, so you can, like, to discretize this in space, you can just take a finite particle approximation, and the resulting trajectory would now be just like mu t is replaced with Dirac deltas. And this can be realized as follows: you draw n samples from some distribution mu naught, and then you just update according to this procedure, update of xt plus 1i as I minus this is gamma h of mu t, exactly h of mu t, just the expectation replaced with mu hat.
I see. So what is happening is that you could not access the integral. So what you're going to do is sample, and then
I'm doing a finite sample approximation, and that exactly gives you SVGD. So this basically tells you that, in fact, as if you take the number of particles n tends to infinity, you'll exactly recover this. So SVGD in the mean field or infinite particle limit is exactly the kernelized Wasserstein gradient descent of the field divergence. So this finally gives you like an explanation of why that whole thing, which had deterministic updates, and that whole black box thing is actually working because it's doing some sort of steepest descent update in this infinite dimensional space.
In some sense, like SVGD, like the particle version, is in fact easier than the integral version.
The particle version is the one you can implement, but the integral version is the one you can interpret and analyze. And the integral version is the one up until now, as Ayush asked, we could give rates for. But we closed this gap, like our work was to close this gap. So yeah, mean field SVGD you can get non-asymptotic in time convergence analysis by iterating through a descent lemma, just like the proof of smooth SGD. But finite particle SVGD, there's a lot of problems here.
So from my understanding, to give guarantees, you need not just T, but how close is the SVGD to SGLD? So you need the number of particles. Like your guarantees will be in terms of both.
Here, like if you're giving guarantees for the mean field, then you're already assumed implicitly that the number of particles is infinite. So time is the only factor there. Time and the dimension shows up due to some reasons. But like this sort of descent lemma strategy, this wouldn't work in the finite particle regime, because in the finite particle setting, mu hat t, if pi star is continuous and mu hat t is just a mixture of Dirac deltas, the scale is always infinite. And moreover, because there's a lot of messy interparticle interactions here, so you can't also just focus on the law of each particle and track it explicitly. And like given a fixed t, the particles I are also not independent of each other. This is sort of bootstrapping.
But you agree, like there is some sort of gap between you sampling from the mean field and the mean field.
Yes. Initially they're the same and then they diverge, and like this is like you can quantify this gap as well. Like one way
It's an open problem to sort of quantify this gap.
you can quantify this gap by like this would be called quantifying the propagation of chaos basically, because initially the mean field and these are same and then like they are diverging because the mean field updates and the finite particle updates are inherently different. So you can prove guarantees that way, but yeah, you'll get something like this poly d over square root log n to the theta 1 over d. So this is like double exponentially slowed and with a curse of dimensionality.
So just to ask the question here, there is chaos because you cannot simply sample from the mean field at each time.
Yes.
But you have to sample from the mean field and then track these particles.
You cannot sample from the mean field at each time, and as time passes, the deviation between the law of the mean field and the law of the finite particle system, they are also diverging in some, like, yeah, you can show that they exponentially diverge in oscillating distance.
Just to give you an idea of time, like we'll try to
Yeah.
cover it.
Covering?
12, 5, 10.
Okay. So clearly the naive version is hard to analyze. And so the idea here, so we ask whether we can approximate the mean field limit a little differently to get proof finite particle variance. So what we notice here is, so we come up with this different stochastic approximation to the mean field limit, is that so in mean field SVGD, there's two quantities to track. There's the vector field inside the push forward, and then there's the law of the particles. So if you use two different set of particles, so the first, which we call virtual particles, to approximate this h mu t, and the second set to approximate mu t, you will avoid those complex you may avoid those complex interparticle dependencies and get a different kind of stochastic approximation. And we saw that this is realized by this kind of dynamics, which we call the lower triangular dynamics, that xts equals xts minus gamma h times xts. And it will interact with only xtt. So it sort of interacts only with the virtual particles. Conditioned on the virtual particles, each real particle stays independent of each other. So if you condition on these gray ones, each blue particle is independent of each other. And that gives you the necessary conditional independence, which would allow you to directly analyze this process without invoking propagation of chaos bounds.
What is the virtual particle?
Virtual particles are what you use to approximate, like there are some initial burn-in particles which are not part of the output, but you are just using them to approximate h mu t. So you use different sets of particles to approximate h mu t and mu t. The discretization SVGD uses to use the same set of particles to approximate both, and we saw that led to a lot of bias and that led to a significant deviation from mean field. We'll see that this is actually just like SGD is a stochastic approximation to GD, and in expectation, the iterates of SGD remain like just doing GD. This has some sort of a similar effect. This is exactly a stochastic approximation to, and yeah, this can be, you can like introduce mini batches and get a tractable algorithm. So what's interesting here is that like conditioned on the virtual particles, the real particles in the future are all independent. So you just track the conditional law of the real particles conditioned on the virtual particles. This is similar to how in the analysis of SGD you track the current interrupt condition of all the past on the you've seen. And
just to get an idea, are these conditional probabilities also part of your P2 of RD? They're all elements like
yes.
The laws are all.
Yeah.
Do the laws, I mean, does the conditioning change the?
You can even show that they all admit a density with respect to pi star. If they admit a density initially, they'll admit a density with respect to pi star every step. Not only they are in P2, they're also absolutely continuous with respect to pi star. And yeah, so this gives you this kind of an algorithm, which we call virtual particle SVGD. And here, like if FT is the filtration of all the virtual particles, of all the real particles, of all the virtual particles seen so far, this GT is a stochastic approximation to h mu t given FT. So if this is gradient descent, this is stochastic gradient descent in the Wasserstein space. So this was the first known, to the best of our knowledge, the first known construction of a stochastic approximation in the Wasserstein space itself. And as we showed that this lower triangular dynamics exactly admits a finite particle realization. So you can track the stochastic approximation using exactly finite particles. So if you want n conditionally ID samples and you run your algorithm for t iterations, you'll need only t capital T plus n particles. And the analysis of this is also very similar in spirit to the analysis of SGD in this infinite dimensional space. And that gives you some nice rates, which is worse than the rates you'd get for mean field SVGD. But mean field is not an actually implementable algorithm. Here you're getting rates for the first time for an actually implementable version. And here we are assuming the kernel is nice enough and like function is smooth and the target is sub-Gaussian. But even if the target has like sub-exponentially decaying tails, they're fine. Like any sub-quadratic tail growth is fine. And in fact, if this extra t is too much for you, we even propose a different algorithm with slightly worse rates, which inputs only n particles and outputs only n particles. We just use a random batch, like we basically instead we are basically random batching the SVGD step, and we show by a coupling argument that this is actually the law of this is actually close to the law of VP SVGD at the virtual particle SVGD at each step without using T extra particles. And using the fact that our outputs are all conditionally independent, like conditioned on the virtual particles, we get very fast finite particle rates, no cursor dimensionality anymore. And yeah, so we get some rates for the virtual particle version and slightly worse rates for the global batch version. But both of these significantly improve on the best known rate. It's a double exponential improvement, and it's the first known rate for this problem, which doesn't suffer from a cursor dimensionality. And it's also the first result that holds for sub-quadratic tail growth. In fact, if you are to compare on the basis of oracle complexity, the only known implementable guarantee has like the leading order oracle complexity is e to the d to the poly d over epsilon square, whereas ours is like d to the 4 over like poly d over epsilon basically. So this is the first known polynomially scaling oracle complexity guarantee for this problem. And the other application which I'll quickly quickly skim through is that you can, using the same Wasserstein gradient flow machinery, you can show that SGLD is actually a stochastic also a stochastic approximation, but to LMC. But like this is a stochastic approximation in path space. And the continuous time no noise version of this, which was the longitudinal diffusion SDE, it's actually a very special. It's actually a particular realization of the Wasserstein gradient flow of the KL divergence. It's an exactly like the SDE process is a realization of the Wasserstein gradient flow, and then you are doing an Euler discretization, so that introduces some bias, and then you are taking stochastic gradient, so that introduces some stochastic approximation error in the path space as opposed to in the measure space. But again, you can use like just the way you could use the theory of Wasserstein gradient flows to analyze longitudinal diffusion. You can carefully account for this. Introduced stochastic approximation noise and use the same machinery of Wasserstein gradient flows to analyze SGLD. In fact, the key idea is that SGLD, what it's doing is it's adding stochastic approximation noise, and it also has this independent Gaussian noise, right? And this stochastic approximation noise is basically zero mean IID average. So the central limit theorem would dictate that this is also approximately normal. So this is like an addition of two normals, which behaves as normal with a larger noise. So the idea is that like SGLD is essentially equal to LMC plus slightly higher, plus some driven by slightly higher and approximately Gaussian noise. And if you see here, since eta is very small, the Gaussian noise part, the exactly Gaussian noise part dominates the stochastic approximation noise. So using a non-asymptotic like by constructing an appropriate non-asymptotic CLT, you can essentially absorb the entire stochastic approximation noise inside the Brownian noise, and then use the machinery of Wasserstein gradient flows to analyze. Yeah, and that's about it. Some open directions here would be like whatever I discussed was restricted to gradient-based optimization, but like you could go beyond gradient-based. Like continuous optimization is much more beyond gradient descent, say proximal point methods and things like that, or mirror descent. Can those tools and techniques be extended? Are there sampling analogs of those tools? For the proximal point method, like for extending proximal point method sampling, there have been some great recent results. Secondly, lower bounds, the theory of lower bounds here is completely open. There are no algorithm-independent lower bounds, and even the algorithm-dependent lower bounds that exist are like very specific, like to Gaussians or to just for Langevin. And yeah, acceleration is something that is also not understood here. Like, what does acceleration even mean? Can you even accelerate? Yeah, and that's about it. Thanks a lot. Yeah.
Clearly, when you show the dependence of the side so do you think those are like optics?
There's no lower bounds in this literature. Like, this is a major question that. I think the exact factors in the polynomial can definitely be improved. The more interesting question here is that do you need some sort of virtual? Would you always need some sort of decoupling to get it down from X to poly, which I think is possibly true. If we could show some so this result is proven by a propagation of chaos bound, that it's quantifying the Wasserstein distance. So if you could somehow prove a propagation of chaos lower bound, that okay, if you use the same set of particles to approximate both, you'll always incur this exponential dependence. Then maybe So it's so nascent at this stage that even understanding whether this X to poly is fundamental. So there's some works that analyze the geometry of the chi-squared. Equipping the space with the Wasserstein metric. Right. You analyze optimization of chi-square, and that would lead to an entirely different gradient flow, but in the same geometry. The other thing you could do is change the geometry of the space itself. You could use some entropy regularized Wasserstein distances and keep KL as is, but that would change the geometry of the space, so the geometry of the problem. Yeah. Yeah. I mean, you can this entire all of the SVGD results can fairly be straightforwardly ported to MMD. The thing is, optimizing MMD doesn't give you a tractable sampling algorithm because you'd have to know some functionals of that are not available in closed form, whereas SVGD is available in closed form. But the entire theory goes through for MMD as is.
So so I'm guessing there is some sort of practical applications of this for Wasserstein gradient flows to diffusion models. So in the coming from a more applied sense, does this result show anything there? Should you be sampling multiple points on that Wasserstein space?
I would like to think so, yes, but this is something we are actually looking into, whether these concepts can be translated to provable guarantees for diffusion models.
And right now there are.
Right now, I think there's some empirical works that play around with this, but don't hold me to it.
I think only in the mean field there's anything.
But
asymptotic mean field.
But the SGLD result that we have there, we actually get some from our analysis, we get some algorithmic tricks that we can use to sort of correct for the noise introduced in each of these steps, and that would just plugging that into diffusion models could give you some benefits. Yes.
And there, sort of in those sort of models, you are happy to converge to any point on the manifold, whereas here you want to converge straight away to.
No, there, from a process point of view, to the best of my understanding, is that you have samples from a given target. What you do is you use a forward process to corrupt it to some known distribution, and then you want to sort of instead of you want to reverse this process, so you don't even have access to F. You don't even have access to the Hamiltonian.
Yes, sir. Yes.
Yeah. It's just samples. So the idea is that whether this backward, like you can use concepts from like these forward process, backward process construction instead of those being like those being SDs, could those be arbitrary trajectories on the space of measures that could be realized via like flows of some IPM? Would that give you something fundamentally different from?
So far, there's been no literature that deals with, say, momentum-based updates, a second-order type update instead of.
It's not known how to achieve acceleration here. It's one of the major like you can so acceleration, by acceleration I just mean acceleration in like the condition number. So you can improve D dependence. So like if you go from overdamped Langevin to underdamped Langevin, you can get D to root D. But so suppose you're dealing with strongly convex F. So the L by it still goes from kappa D to kappa root D. So how to actually get to root kappa is not understood.
So if there are no more questions, we can end the speaker. You have a question of. So we have lunch available at the launch. Okay, but